All right, so here's example 4.5, number 7. And I like this example because it really kind of pulls together a lot of the things we've been talking about so far with regards to different kinds of vectors, how displacement is related to velocity, and velocity is related to acceleration, and unit vectors, and all that stuff. So what we have here is a car that is going at a constant speed of 12 meters per second. All right. Now it's a constant speed, not a constant velocity, because look, as we're told, look a little further down here, it's going around a quarter of a revolution. All right, it's going around a curve, a quarter of the way around a curve. So what we're asked to find is the average acceleration that the car experiences. All right, what would cause a car to go from going straight to being bent around a curve a quarter of the way? And now we're told that it goes a quarter way around a curve, but we're also told this by its position unit vectors as well. Think of it like this, okay? The car, let's say that right here is our origin. All right, we're told that the initial position is 76.4 meters y hat. That is, there's no x hat. All right, so that means it's 76.4 meters in the y direction. So the car is starting here. Okay, 76.4 meters from the origin, and it winds up its final position. Excuse me. Its final position is 76.4 meters x hat, which is over here. All right, so that change, or those two different positions, and the change in position tells us that the car is doing this, taking this path as it goes around the curve, right there. All right, so even if we weren't told that it goes around a curve, we could have figured that out by the change in position. All right, so I'm going to move to the next slide where there's some more space, and we're going to keep in mind that it's got a constant speed of 12 meters per second. So that's 12 meters per second, and so is this right here. I should call that velocity final equals 12 meters per second, and this is velocity initial right here. But you'll see that they're going different directions. All right, so what kind of acceleration would cause that to happen? All right, we're going to kind of restart this on the next slide. All right, so I've got my, and again, remember we're asked to find the final acceleration in unit vector notation. All right, I'm going to try not to hog up too much space right here. I'll make it a little bit smaller. All right, here's my car going around a curve like so. Just like that, okay? Now, the initial velocity, the velocity initial, and the velocity final are different velocities because they're different directions. But as you recall, the magnitude was the same. All right, the car is going at a constant 12 meters per second. So let's write this down in unit vector notation. All right, this velocity right here. The velocity initial is, well, right here, what is it? It's 12 meters per second in the x hat direction, right? And how is it traveling in the y hat direction? Well, nothing, right? Nothing in the y hat direction because it's going all in the x right here. So we're going to say, all right, and 0 meters per second y hat. All right, fair enough. And then the final velocity, the v final, equals what? All right, well, it is, after it is done going around this curve right here, it is now going in this direction, which appears to be the negative y direction, right? And not at all in the x direction right here. So we've got 0 motion, or 0 meters per second in the x hat direction. And we have what in the y? Well, we've got negative 12 meters per second in the y hat direction, right? That's a negative sign right there. Negative 12 meters per second in the y hat direction. Okay, it's important that we write these out because we need to find the change in velocity, which will help us to find the change or the acceleration. Remember that acceleration, or average acceleration, equals a change in velocity over a change in time. All right, we have our change in time. We're told that is 10 seconds, right? Delta t equals 10 seconds. So all we need to know is find out what is a change in velocity right here, and let's divide that by time. Okay, so let's determine our delta v, our change in velocity. So it is really v final minus, my minus signs are lacking today, minus v initial, right? Now let's see if I can squeeze this in after that line right there. So we're going to subtract, we're going to use unit vectors to subtract the v initial from the v final. So that should look like this. So for the x hat direction, we've got 0 minus 12, that's not a 12, that's a 2. 0 minus 12 meters per second, that's x hat, okay? And we have what in the y direction right here? Well, we've got negative 12 minus 0. Negative 12 minus 0 in the y hat direction right there. All right, let's simplify that, okay? So our delta v, or change in velocity vector, is going to be negative 12 meters per second x hat and negative 12 meters per second y hat. Okay, so to go from a velocity in this direction to a velocity in that direction right there, that means we need to have a change in velocity that is directed towards the center. All right, if you were to take this initial vector right here, this initial velocity vector, and kind of pull it that way, call that delta v. All right, that would result in this arrow turning, so it winds up being this arrow right there. So the change in velocity can be thought of as being directed towards the center of that arc. Now I'm going to dotted line box that. Okay. Like so. It's not our final answer, but it will help us to get our final answer because, as we stated before, our average acceleration equals a change in velocity over change in time. Well, actually, it's become really easy for us now because all we need to do is take our velocity and divide it by time, right? Delta v, that vector, divided by time, which is a scalar right here. I know I just wrote that right up above there. So let's write this out in unit vector form and then divide by time. So negative 12 meters per second x hat and negative 12 meters per second in the y hat direction. That's coming from right up here, okay? We're going to take that, we're going to divide that by time. So that's 10 seconds and 10 seconds. All right, we've got a change in velocity in the x direction and a change in velocity of the y in the y direction. Yes, and both of those are divided by 10. All right, so let's just simplify right here and see what we get. So 12 divided by 10, or well, negative 12 divided by 10. That should be 1.2, right? 1.2, what are our units? Meters per second, right? Or meters per second squared. Meters per second squared. Oh, and you know what I forgot? I forgot my minus sign right there. All right, negative 1.2 meters per second squared x hat, and the same thing, negative 1.2 meters per second squared meters per second squared in the y hat direction right there. That is our answer for our acceleration in unit vector form right there. All right, we've taken the change in velocity and divided it by time. We just did it in the x direction and in the y direction right here. And now we have our unit vector value for acceleration. So let's see if it actually matches up with our change in acceleration. All right, or we're going to get this in unit vector notation and in magnitude and direction notation right here. So let's see what we get. All right, so what is our magnitude of our average acceleration right here? Well, it's going to be negative 1.2 squared. Remember, we're using the Pythagorean here to get our full magnitude, and plus negative 1.2 squared, which gives us a magnitude of 1.7. All right, 1.7. I'm rounding it to what? 1.27. Oh, sorry, 1.7 what? Meters per second squared, right? Because it's acceleration. All right. What's our direction? We find our direction theta by taking the inverse tangent of 1.2 over 1.2. Remember, we're using absolute values. You could probably have called this one, all right, the equal legs mean that usually the angle is going to be 45 degrees, and that's what you would get if you calculated out the inverse tangent. So again, you would come to this point and you'd say, okay, 45 degrees, what of what? All right, well, we got a negative x and a negative y right here, so that would be south of west. So our average acceleration is going to be 1.7 meters per second squared at 45 degrees south of west. That's our magnitude and direction notation right there. And that should match up very well up here with our change in velocity. All right, as we said before, the change in velocity is always in the same direction as the acceleration, or the average acceleration, because they're related just by a factor of time. Okay, so this is example 4.5, number 7, two-dimensional acceleration. We have an acceleration being applied in the x direction and in the y direction right here. But all these are added together, and these algebra operations are done very easily by using unit vector notation right here. It's taking the x component and the y component separately and doing mathematical operations that way. So I hope that helped. Please come to me if you have any questions, and I'll see you on the next one. Thanks for watching.